Hi students, Professor Gray here. I have a supplemental video for you guys for the Ideal Gas Law Lab. So I've broken up the worksheet into a couple of slides here so we can talk about it. Now on the video, you would have seen that your mass of sulfonic acid for the first trial was 0.15 grams, and then the mass of sodium nitrate was 0.14 grams, and then you would have seen those two things put together in a vial and it would have created some gas. And the burette had an initial volume of water in it of this right here. Now, this burette reading, it's upside down. So you can see how at the bottom here we have 10, and then we have 9, 8, 7, 6, 5, 4, 3, 2, and 1. So what you're going to do is you're going to read it this way. So that's going to be 2 point something milliliters. So say we call it 2.8 milliliters because the procedure told us to record it to the tenths place, which is where the 8 is. And then you guys are going to convert it to liters. So you should know how to convert from milliliters to liters. Now, again, don't take my word for it. You guys read the burette and get your own reading off of it. Now, the next line says the final volume. And this one's a little bit harder to see, but to me it looks like it's right about there. So you guys go ahead and enlarge the video and see what your reading is. And I'm just going to guess maybe it's 45.1 milliliters. And then I'm going to need to convert that to liters because in our gas laws, we always use liters. Now it says the net volume of nitrogen evolved because this reaction is giving off nitrogen gas. So the nitrogen gas given off from the reaction goes into the burette right here and it pushes the water out and it fills up this volume here. So what we want to do is take the final volume and we're going to subtract off the initial volume. So we've got 45.1 milliliters minus 2.8 milliliters, and that is going to give us some value in milliliters, and we're going to convert that up here into liters. So maybe we do all of that and we get 0.0423 liters, okay? So I didn't do that math for you because you guys should know how to convert from milliliters to liters. So I'm just going to leave it like that, okay? And then you guys will do trial 2 and it'll be exactly the same thing. Alrighty. So then we go on to finding the room temperature, and you guys are shown a thermometer, a very large thermometer, and it's going to give you temperatures in Celsius and Fahrenheit. In the gas laws, we do temperature in Kelvin, so you're going to have to convert. So say you look at the thermometer and you decide that you have 21.3 degrees Celsius. Well, you're going to have to add 273 or 273.15 to your 21.3 to get your temperature in Kelvin. And say I did that with my made up temperature of 21.3 and I get 294.5. And I stopped in the tenths column because we are adding here, so we have the addition and subtraction significant digit rules. So if you added 273.15, the 21.3 value only goes to the tenths, whereas the 273.15 goes to the hundredths, so you're going to stop in the tenths place according to the significant digit rules for adding and subtracting. Okay, the barometric pressure. So you're shown a circular barometer, and the circular barometer gives you the barometric pressure in various units. But the one you're going to want to look at is the centimeters of mercury. And I'm just going to give this a guess and put that maybe we got 73.00 centimeters of mercury. And you guys are going to have to convert that into millimeters of mercury. So you're going to have to know how many millimeters are in a centimeter and do that conversion. Now, there's a very, very easy conversion between millimeters of mercury and torr, and I'll let you think about that for a second. Now, the next line says the vapor pressure of water. Okay, so here's the thing. So say we have a bottle, and you'll have to excuse the cat meowing in the background. I have a stray cat who likes to go through our cat door and come in our house. And then he likes to scream to see if he can find someone to give him some scratchies. So yeah, I'm doing a lecture right now, so I can't pet him, so he'll probably be screaming a little bit more. So anyways, say you have a bottle of water, and on top of the liquid water you have a gas, which we usually do, and it's usually air. But say that it's nitrogen like we have in this lab. Okay, so nitrogen gas, that's a diatomic molecule, meaning there's two atoms. So there's two atoms of nitrogen bonded together, and that makes N2, and that is nitrogen gas. Well, above that, you're also going to have some water vapor. So that's water in the gas form. So right here, this is asking for what's the vapor pressure of that gaseous water above the liquid water at the temperature that we're at. So what we do is we look up this chart, which was in the procedure portion of this lab. You clicked on the link and it took you there. And what you do is you find the temperature in Celsius. So we would go down this row and we would go to 21.3. And we would see that we are at 18.996 torr. Okay, so we've got 18.996 torr, and that's going to be what in millimeters of mercury? Really super easy conversion. That's going to be 18.996 millimeters of mercury, okay? Now, the next slide says moles of nitrogen evolved. So we've got to switch gears here for a second, and we've got to calculate a limiting reagent problem. So we've got to find the theoretical yields, and in that we've got to find what's the limiting reagent and what is the excess. So back to the very beginning of this lab, we've got ideal gas law and molar volume of nitrogen, and then below it, it's telling us that we are reacting sulfonic acid with sodium nitrate. And then we did this part of it to watch it go. But for the reaction portion of it, we're going to need to write out the balanced equation. So what we do for that is we're going to say, okay, I've got sodium, I think I've been saying sodium nitrate when it's actually sodium nitrite, and there's a difference there, bad teacher, bad, okay? So we have sodium nitrite, which is the O2 version, and nitrate is NO3. And we dissolve that in water, so we've got AQ there. And to that, we are going to add sulfonic acid, which is H3NO3, also dissolved in water. And I'll put the little space there for our coefficients. And what that is going to give us is sodium bisulfate and some nitrogen gas. And it's going to give us some water. And the water is in the liquid form, so that's a fancy L right there. And if we look at all of our atoms and we balance them, we will find that we have coefficients of 1 all the way through. So that isn't too exciting there. Or it might be really exciting to you because it's not hard. So now what we have to do is we have to do some calculations. So I'm going to go ahead and go back up here and go, okay, I started with 0.15 grams of sulfonic acid. So I'm going to write 0.15 grams of sulfonic acid, and I'm just going to abbreviate that SA. So that's this stuff right here. And whenever I'm in grams, I want to go to moles. So 1 mole of sulfonic acid is some mass of sulfonic acid. And so I would add up those 3 hydrogens and the nitrogen in the 3 oxygens, and I'd come up with 97.1. Now I'm in moles of sulfonic acid because our grams of sulfonic acid can cancel out. And I don't want moles of sulfonic acid, I want moles of nitrogen. So I'm going to put moles of sulfonic acid on the bottom here. So the one on the top there and the one on the bottom there will cancel out. And where I want to go to is moles of nitrogen. And remember, the nitrogen that we're talking about is the diatomic molecule N2. So where do we get the numbers that go next to mole of nitrogen and mole of sulfonic acid? I get them right off of the balanced equation, and we've practiced this before. So for every 1 mole of sulfonic acid that you react, you're going to produce 1 mole of nitrogen. And you don't need to go all the way through to grams on this one because you're just trying to see how much is evolved so you can figure out which one is the limiting reactant. And the answer up here, or the line up here, only asks you for moles. So we do need moles. So you're going to do that calculation, and you're going to get some number of moles of N2. So whatever number you get there, you're going to put on up here in that spot if it's the limiting, if sulfonic acid is the limiting reactant, but you don't know that yet. So you're going to go back and you're going to go, there's more to that part of the lab. And what is next? Well, you have to calculate how much nitrogen you can make if you use the, oh my goodness, bad teacher, bad. What on earth? Come on, there we go. All right. If we use that 1 mole of sodium nitrite. So let me write this back here. There we go. Okay. All right. So what we had is we have 0.14 grams of sodium nitrite. So we write that right here. Sodium nitrite. And we want to get rid of grams of sodium nitrite. And we want to go to moles of sodium nitrite. And then we'd have to add up sodium, nitrogen, and 2 oxygens. And what we would come up with is 68.995. And then, like I said, we're going to use the coefficient, that 1 mole of sodium nitrite down there. And we're going to say for every 1 mole of sodium nitrite that we consume in this reaction, how many moles of nitrogen gas do we produce? And that's 1. And we've got those numbers, those coefficients 1 and 1, right off the balanced equation. So that gives us 1 mole of N2 on the top, and grams of sodium nitrite cancel out, and moles of sodium nitrite cancels out, and you're left with some number value, moles of nitrogen gas. And we're going to call that Z, just to indicate that it's different from the number that is the X value. So Z moles of N2. Okay. Now we can finally write a number right here for moles of nitrogen evolved. So what you're going to do is you're going to look at the number X and you're going to look at the number Z. And whichever one of those is less, that's going to be your theoretical yield. Okay, so say X was the lower number, then you would put X moles of N2 right here in this box. If Z was a lower number, you'd put Z there. Now, if X is a lower number, then you would say that sulfonic acid is the what kind of reactant? Then you would say that sulfonic acid was the limiting reactant and sodium nitrate is the excess. If Z is the lower number, then you're going to call sodium nitrite the lower number, the limiting reactant, and you're going to call sulfonic acid the excess reactant or reagent. Alrighty, so that's how we calculate that portion. Now, the molar volume of nitrogen. The molar volume of nitrogen is going to be the volume of your nitrogen back here, so 0.0423 liters, divided by whatever value is up here. So say we decided that X was the lower number, and that was going to be the maximum amount of nitrogen gas that we could make, and so that's the theoretical yield. So you're going to put that on the bottom there, X mole of N2. Now remember, I made up the 0.0423 liters because I made up this value and this value. I just looked over here and here and I made a guess, but you guys are going to make a better guess, okay? So don't just copy what I write. Get your own values. And so you guys are going to do 0.0423 divided by whatever number X is, and you're going to come up with a value. And let's just call that value W, so it's different from X and Z. And the units on that will be liters over moles of N2. So that's how you do the molar volume of the nitrogen. Now, the next line says pressure of dry nitrogen gas, and that's going to bring us back to this bottle example right here. So that's why I left it there. Now, the pressure that you guys are reading on the barometer, so that was that circular gauge that we looked at up here. What happens is the pressure of the barometer, the pressure reading on that, is going to be equal to the pressure of your nitrogen gas that's up here. So I'll just go ahead and put gas there, plus the pressure of the water vapor. So the pressure of the dry nitrogen gas, which means the nitrogen without the water in there, so the pressure of the nitrogen gas is going to be the pressure of the barometer minus the pressure of the water vapor. And you guys are going to do the calculation on that. Okay, so the pressure of the nitrogen gas That's going to be the pressure of the barometer, and say we got 730 millimeters of mercury from our barometer. We would subtract this value right here. So that is the water vapor pressure at whatever temperature we have. So we do minus 18.996 millimeters of mercury. And again, you guys remember, I just made up those values because I want you to read the instruments yourself. Okay, I'm just showing you how to do the calculations. So that's going to give us 711.0 millimeters of mercury, and that is the value that you would write in right there. Alrighty, moving on. So we just did this one. Now we're going to do experimental ideal gas constant, the R. So what we have to remember is that PV equals nRT. So right here, you guys are calculating for R. So you have to do the magic of algebra and rearrange this equation, and you're going to get that R is equal to PV over NT. Now, you have all of these values in the charts that you have just filled in, but what I want to point out here is this P right here. This is the partial pressure of your nitrogen gas. So if we just do a little bit of plugging and chugging, what we had was 711 millimeters of mercury for the partial pressure of our nitrogen gas, and the volume of our gas we had was 0.0423 liters, and we divided that by X moles of nitrogen gas. Remember, you have to calculate the value of X, okay? And then we had 294.5 Kelvin, and you do all of that math, and what you're going to end up with is a very large unit, because that's how R is, and it's going to have 4 units in it. So it's going to have millimeters of mercury times liters divided by moles and divided by Kelvin. And that answer is going to go right there. And then you will do that entire thing again for trial 2, and you will calculate another R value. Then you will take those 2 values and you will add them together and divide by 2 to get an average R value. Then you guys are going to get a percent error. So say that you got 60, say your R value was 65.43 millimeters of mercury times liters over mole times Kelvin. All right. So the way that you would do percent error is you're going to do the absolute value of the theoretical R value minus the experimental value. And the experimental value is the value that you got in your experiment, okay? So say your average R value, those 2 together, adding them up, divided by 2 is 65.43. That would be the experimental. And then you're going to divide that by the theoretical value, which sounds really strange because you're using the theoretical value twice, but that's how we do it. And you're going to multiply that by 100. So the theoretical value for R is 62.36 millimeters of mercury times liters divided by moles times Kelvin. So how we would do the percent error for this made up value right here is we'd say that our percent error is equal to the absolute value of the theoretical, which is 62.36, and all of the units are going to cancel out, so I'm going to leave it off just to save some space here. And you're going to subtract the experimental value, and you're going to divide that by the theoretical value, and you're going to multiply that all by 100. And you're not going to worry about the fact that you have 62-ish minus 65-ish, and that's going to create a negative value because you have put absolute value bars around that. And the absolute value bars say whatever is inside, whether it's positive or negative, it comes out positive, okay? So don't worry about that. And then some books or some instructors will have experimental minus theoretical. It does not matter when you throw absolute value bars around it because it will come out the same positive number. Okay, so you do 62.36 minus 65.42 divided by 62.36, and you're going to get some kind of value there. I have not done the math on it, but if you are under 10%, usually that is pretty good, okay? All right, you guys, so that's how you do the math on this lab, and yes, there were a lot of steps here. So hopefully this helped you, and I will see you in the next lecture. Bye-bye.